notation things, x bar for our sample mean, mu for population mean, so those are the difference between those. In a lot of cases tonight, we'll be using x bar to approximate mu. That's a very common thing. It's also in your textbook. So a quick problem just for reference, back to basics, calculating mean real quick. So we have a set of different Orlando City players from the 2015 season, names, and then the number of goals scored. So if we want the mean number of goals scored, we just do what? We add up all the numbers and divide by the number of numbers we have. So we have 4 here, 3 here, 3 here. So 6 and 4 will be 10. So we'll add up all these numbers. They total to 40 over 10, which means our sample's mean will be 4. Okay? And if you have questions about any of my notation, just let me know. I know a lot of professors use some different notation. Another disclaimer, formulas and things like that might be a little bit different than what you've seen. Just roll with me. It's okay if it's not what your professor would do. I always say to check with your professor whether we get to confidence intervals or hypothesis testing when we have different t-tests or a test with z. Some professors have different qualifications for what we would do what test with, whether we know sigma or don't know sigma, and those sorts of things. So that's at your discretion, but for the sake of the review, just roll with me and we'll just do it the way I've done it in the past. Quick note, this might come up as a question. The value of your mean for your sample does not have to be possible in your data set. So a good example is this problem. Our mean worked out to 4, and I don't see any data number here at all that comes out to 4, right? So just because your mean is 4 doesn't mean you had to have a 4 in the data set. That makes sense? Cool. Onward and upward. Okay, so looking at variability, just a couple of definition things. Variability is a measure of spread, right? So we're looking at how tight the groupings are on measurements. Range, just difference between highest and lowest numbers. So if I give you this data set and we want the range, we're going to find the highest number on here, which looks like we have 49. And the lowest, let's see, we have -12. That's pretty low. So the difference in those, we'll have 49 minus -12, which gives us 61 for the range. Mean, similar thing. I ran it in my calculator, and I got 12.3 repeating for x bar. So that's just all these numbers added up and then divided. Simple stuff. I'm trying to go fast because I want to get to the meat of the course and not simple stuff, but we'll keep it going. Sample variance, s squared. Sample standard deviation, s. Those are just definitions, right? S squared for variance. This is one way I've seen it written. Your book might have other ways to write this depending on how big your sample is, or there are other approximations we can use, but this is my go-to guy for calculating sample variance. So if you're asked, common mistake on an exam, if you're asked to calculate sample standard deviation, you might forget to take the square root of that whole thing at the end, right? This side here, you got to take a root so that you get s, right? We want to end up with s. We need to do this, all this math, and then take the square root. So this is just difference between each of your x's and the sample mean, quantity squared divided by total number of values you have minus 1. Okay, so from there, quick practice problem. I'll just write some quick stuff out. I'll just give you x bar equals 2 for this data set. We're just going to calculate variance real quick. So s squared will have 2 minus 2 squared plus 2 minus 2 squared plus 5 minus 2 squared. I'm just taking each of the individual x's and subtracting that mean, squaring them, plus 0 minus 2 squared, 1 minus 2 squared. And that'll all be over n minus 1, and our n is 5 here, 5 minus 1. And so that s squared will come out to 3.5, and that's our sample variance. And this can be helpful when you get into problems later on if you're required to calculate variance in order to use it for some sort of a test statistic. For a hypothesis test, that's a very common thing. But it's also possible that you'd be given the sample variance to then use in the test. So just be prepared for anything. And then if we want s, that'll be the root of s squared, which will be the root of 3.5. So we'll get 1.87 approximately, okay? Any questions on that? Very good. Quick little review on population variance, population standard deviation. We use sigma. Sorry for my ugly handwriting. Hopefully you can follow it and read. If something looks wrong or you don't know what it means, just tell me and I'll try to explain what I wrote. If not, we'll be in good shape. So sigma squared here for population variance, sigma for population standard deviation. Onward to Chebyshev's rule. So if you remember with Chebyshev's rule, we really only use this when we don't know the shape of our distribution. Because this is not as good of an approximation as empirical rule is. This guy's really useful if we know that we have a mound-shaped symmetrical distribution. We can get more information out of the graph. So Chebyshev's rule, 1 minus 1 over k squared, where this guy is just the number of standard deviations we are from the mean on both sides. And so that number that we get from plugging in k to this will give us the percentage of measurements we expect within that many standard deviations of the mean. So if we say, if we're 2 standard deviations away here, here's our mean, this will be plus 2s, minus 2s. If we're within 2, my k is going to be 2. And this is just normal, but we don't know that it's normal, of course. So if we plug in 2 there, we get 1 minus 1 over 2 squared, which is 4, which is 3/4. So we would expect 3/4 of our measurements to lie within 2 standard deviations of the mean. Some people memorize some of these numbers. For 2, that'll be 3/4. For 3, you'd have 1 over 3 squared, so 8/9 would be your number. And sometimes people memorize these. You don't have to. If you just remember this guy, you're good. And we know that we have to have a k greater than 1. I've seen textbook problems and practice problems where they will ask you, what can we say about the data within 1 standard deviation of the mean? And they don't tell you it's normally distributed. And if you don't know it's normal, then you have to use Chebyshev's rule. And if we plug 1 into this guy, you're just going to get 0, which doesn't make any sense, right? We know there's something there within 1 standard deviation. So we need to have a k bigger than 1 in order to keep this whole term from being non-zero. So just keep that in mind. If they ask you, and this is a straight textbook answer, if they ask you what's within 1 standard deviation and you have to use Chebyshev's rule, you just say, I don't know. And that's it. Okay? So, yeah, sure. K equals 2. K equals 2. K standard deviations from the mean. So your k can be... Yeah, I was just giving an example. K does not have to be 2. It can be 3, it could be 30, it could be anything. I could say k equals 6. We're 6 standard deviations left and right of the mean. If we plug 6 in, we get 1 minus 1 over 36. So 35/36 of your data would lie within 6 standard deviations of the mean. Does that make sense? Okay, very good. And so we can make inferences based on that data in terms of the spread or where we might expect to find certain values, and that's all without knowing the shape of the distribution. Empirical rule tends to be much more useful, especially when we know we're mound-shaped and symmetrical. That's your key word. That's like a trigger word to know we're talking about empirical rule. You guys know more than this, obviously, with your normal distributions. You can read your tables and all of that good stuff. But for a quick estimation, this is really nice. So for these approximations here, if we have our mean in the middle, and we know that we have, if we're 1 standard deviation left and right, then we know in here we have 68%, so 34% on each side. If we go another standard deviation out, 2 standard deviations left and right, then between those, 95%. I'm sorry this is sloppy. There are plenty of charts online and in your book. This is really all you need to know. If you need just one side, you of course divide that number by 2, and that'll be 2 standard deviations to the right or to the left. And then this is a big one. Usually you're not looking further than 3 standard deviations past the mean. Some books and images do go further than that, but rarely will you be asked a question on that. So that's pretty much empirical rule. We'll do a quick practice problem just to reinforce it, but those are our main rules we'll be working with. And then we have z-scores. We all remember we've used this like a zillion times this semester. Z-score being our observation minus the mean over standard deviation. And we'll be using this, so I'm not going to bother explaining. Maybe, if I have the pages in the right order. I will just show you these guys so that we can run through them real quick, because I know I don't want to spend a lot of time on empirical and Chebyshev. So if we have the poor job of looking at cars going through an intersection, which sounds really exciting, basically this dude sat and watched cars. So the mean of the data was this many per day going through the intersection, and we wanted to determine percentage of days that more than 425 use the intersection, and they told us standard deviation is 25. So they're asking, what do we know about the range 325 to 425? What percentage of these days did we have this range of cars coming through the intersection? And this is our keyword, assume you know nothing. So what rule do we have to use? Chebby Chebs, very good. So between 325 and 425, we're probably going to want to make a quick z-score. And if you can't ever see, just yell at me and I'll zoom in a little bit here. Sorry, it's my bad. We want to make a quick z-score, observation minus the mean over standard deviation. So we'll do the left number here and then the right number. So of 325, the mean was what? We had right here 375. Divided by standard deviation of 25 gives us a score of -2, right? And then for the other side, we have 425 minus the mean over standard deviation gives us +2. So we know we are within 2 standard deviations of the mean. Mean plus 2 standard deviations minus 2 standard deviations, right? So we want that area, essentially. But we don't know that it's normal, so we're using Chebby Chebs, like you guys said. So our k is 2, and we remember the rule is 1 minus 1 over k squared, which will give us exactly what we had before, 3/4. Now, the tricky thing about the 3/4 that we have here is that it's not just 3/4 or approximately 3/4. The rule tells us that this is at least 3/4 of our observations in this range. So it could really be all of it. He might have never seen a day where less than 325 or more than 425 vehicles went through the intersection. We just know it's got to be at least 3/4, okay? And that means when we look at part B here, we're going to say, what can we say about the percentage of days more than 425 use the intersection? So we just looked at within 2 standard deviations. Sorry for my wonderfully symmetrical graph here. 2 standard deviations, and we know that the x corresponding with 2 standard deviations above was 425, right? So they're now asking, what's the area here? What do we know about more than 425 cars using the intersection in a day? And we already said this is at least 3/4, right? That's got to be at least 3/4. So what do we have left? We have at maximum 1/4 left. We could have, you know, an eighth here and an eighth here if it was perfectly symmetrical. We could have nothing here and all of it here, a whole fourth, or it could be anything in between, right? So we will say that we have at most 1/4 of our observations above 425 cars, okay? So a fourth of the days he was out there, at most 1/4 of the days he was out there, they saw more than 425 cars going through the intersection. We would say the same thing if they asked less than 325 cars, right back up here. It would be the same thing because we're the same number of standard deviations away. Is that making sense? Yeah? Good, good. So now we say, whoa, now we know this is mound-shaped. So what rule can we use? Empirical. Awesome. So if we know it's empirical rule, we already did our z-scores up here. We know we're within 2 standard deviations of the mean. Does anyone remember the percentage for within 2 standard deviations of the mean? 95. Beautiful. So 95%. And this is an approximation, right? So we say approximately 95%. Okay? And we used empirical rule because we know it's mound-shaped. And then for part B, it said above, again, we're above 2 standard deviations away on that graph. That means if we're at 2 standard deviations, they want to know this area. We just said that we had 95% in there, which means we have 5% left overall to throw around in the other 2. And we know this is a mound-shaped distribution, so we're perfectly symmetrical, which means 5%, half of it is going to be on each side, leaving us with 2.5% above the 425 car mark going through the intersection. So 2.5% of the days he was out there, right? He saw more than 425 cars through the intersection, knowing that it's a mound-shaped distribution. Okay? I'm not going to bore you too much. This one is a very similar problem. We're just, instead of 325, we're at 300, so we're left 3 standard deviations, and we're up 2 standard deviations, same as last time. So you do some math, and you get like 97.35%. You just basically change the numbers you're using depending on your book, and they should be really, really, really close to that within a few decimal places, okay? Most of them are on the same page with that. Cool? All right. All right, one of our main events here, probability. Who had a really good time with their probability exam this semester? Yeah, me too. So if we're looking at this problem, make sure we can all read it. Is that good for everyone? Awesome. So a professor assigns 5 problems to be completed as homework at the next class meeting. 2 of the 5 problems will be selected at random and collected for grading. You have only completed the first 3 problems because we are awesome students, right? So what is the sample space for the chance experiment of selecting 2 problems at random? And so we can think of these as problems A, B, C, D, and E, right? We have 5 problems. So one selection could be problems A and B that you did, or he's going to select, or it could be DC, and we just have to find out what our sample space is. So for part A here, the sample space, we have 5 problems going on. So we have problems A, B, C, D, E. That's what we'll call them. We could have done problems A and B. We could have done problems A and C, A and D, A and E, following, and B and C, B, D, B, E, C, D, C, E, D, E. So basically, I just wrote all the combinations we can possibly have if I did 2 problems, or the problems he's going to select. He's selecting 2. So those are the different combos we can have, of course, if we're not selecting one more than once. So now in part B, they want to know, are the outcomes in the space equally likely? Yeah, they're equally likely because each of these problems has the same probability of being selected. He's just picking 2. Nothing has a greater chance of being selected over anything else. So all those are independent. So we're going to say yes for part B. They are definitely equally likely, all these choices. Part C, they want to know what's the probability that you'll be able to turn in both of the problems selected. In other words, you got to get lucky. So let's say we did problems. What problems do we want to do? We did 3 of the problems. So let's say we did A, B, and C. So those are the only ones we did. We didn't get to do D and E because we had to go to bed because all of us get so much sleep, right? So we did problems A, B, and C. So we need him to pick pairs in which we have done all of the problems in the pair. So the pair can either be A, B. Oh, if he does A, B, we got that one, right? We definitely did A and B. A and C, we also did that. Another one, we didn't do AD, but we did do BC. We did that one as well. And none of the other ones will have both of ours in it, right? We won't have a pair. So we have 3 possible options out of these 10 things where if he picks that pair, we're good to go, right? So we basically just list it as 3 out of the 10 options where we are successful, which will be 0.3. Done. That's your probability, okay? Part D, let's see what they say. Probability would return in both. Change if you have completed the last 3 problems instead of the first 3 problems. So what do you guys think? Do you think that our probability is going to change whether we did C, D, and E instead of A, B, and C, or should it remain the same? Same. Very good, because these are all independent events. It didn't matter if I did B, C, D, or C, D, A, or it's irrelevant. So we're going to say no. Same number of available pairings. So we're good to go on that end. And then let's see what happens to the probability that you'll be able to turn in both problems if you had completed 4 of the problems instead of just 3. So it's actually going to double from 3/10 rather, to 6/10. And we can take a look at this. Let's say we also did problem D. So we still have what we had before, where those pairs apply. Now we could also have done AD. That one's good. What else? BD, we'd done both of those. CD, we also did both of those. 1, 2, 3, 4, 5, 6 out of 10. Crazy cool, right? So maybe it pays off to do another problem, and then you have a pretty good shot if they're only picking 2. So that's our part E answer there. Okay? Problem makes sense? Not too crazy? Yeah. Of course we can. You guys, I'm assuming, have the words in front of you. Everybody good? All right, and I will, just so you guys know, I will be releasing a solutions manual that has all of basically what you see me writing in this exact packet. It'll just be the same packet, but with all of the work done for you, and you'll see my math and my answers, and that way you have that with you as well. So if you're scrambling to write stuff down, don't worry about it. It'll be up in like, as soon as we're done, I'm gonna post it. So that'll be there for you guys, okay? Cool. Moving on with probability. So a bank's offering adjustable rate and fixed rate mortgage loans on residential properties classified into 3 categories: single family houses, condominiums, and multifamily dwellings. Lovely. Each loan made in 2010 classified according to the type of mortgage and type of property, giving us the following table. So there we want to know a chance experiment of selecting one of these 3,750 loans at random. So our total here, grand total 3,750 for the total number of loans that they have. So in part A, we want to know what's the probability that the selected loan will be for an adjustable rate mortgage. Now, if we have an adjustable rate mortgage, that will put us in this column right here. That blocks us off here. So the total number of adjustable rate mortgages, because that's our only category listed, out of the total number of mortgages offered, it'll just be, just like it says, 2625 out of 3750. Sometimes on exams, you'll see an answer left just like this as a fraction. Yes? I'm sorry? Yeah, this packet's online. Study Union website, I believe it's ucfstudyunion.wordpress.com. There's a statistics tab, and then you'll see my name. It's in white, Study Union packet. Just click it, it opens as a PDF. Yeah, of course. So I was saying that you can sometimes see answer choices left as that, just as a fraction, or maybe all the answer choices are decimals, in which case just divide it and then make your life easy, look for the decimal, and you win. Good job. So in part B here, what's the probability that the selected loan will be for a multifamily property? So our multifamily property is, again, pretty obvious. If we're multifamily, we're here. Total multifamily, 710 out of 3750. Ta-da, you're done, okay? And then on this guy, I had some other parts listed for different things we can do with this. So I could say, you know, what's the probability of being in a condo given that you got a fixed rate mortgage, right? So that would be condo given fixed rate. In which case, we're looking at the fixed rate here. We know we got a fixed rate, and we know we're in a condo. So we need to work with those probabilities. If we had a condo with a fixed rate, that's the intersection of condo and fixed rate, right? At 377 out of the total number of fixed rate mortgages of 1125. So we don't really think about it much when we do that, but there's a rule that we're applying where we have the intersection of these two divided by just this guy. So we really looked at the intersection of condo and fixed rate. And this is a property, most of you I'm sure have it on your reference sheets, over just probability of fixed rate. And so what happens is they both end up with a common denominator that cancels out, and then we're just left with that normal guy we see there. Okay? Cool. Wonderful charts. These are always fun. So I prepared this little 3-bodied Venn diagram for us, and we're basically just looking at this TV company and what they reported to us with regard to some of their services. So they told us all these numbers that are very, very interesting. No one really cares about them, but we care about them, right? So basically they ask us all these questions about it, and we have to interpret it. The problem is that these are kind of jumbled. We don't really know what we're looking at. And so usually the best course of action is to kind of start with this diagram. Now, the reason it has 3 circles is because we are talking about 3 services. Notice that there's a TV service, an internet service, and a phone service, right? So when I start to construct these diagrams, what I like to do, and what I find is the easiest way to do this, is to start at the middle with the most specific thing. So if we're in the middle here, that means we've got all 3 services. And they gave us these percentages, but I can just say whatever. We had a sample size of 100. That way, whatever percent they give me, I'm just going to write that number, okay? Because they didn't give me any other numbers, so it's not really going to matter. So they said 15% of the customers have all 3 services, so I'll write a 15 there. Now, what else can we look at? We can look at 23% of the customers subscribing to internet and phone. What else do they tell me here? That's a lot of numbers. 21 to TV and phone service. So they give us a couple of different things. If there are 21, let's look at this guy. If there are 21 in TV and phone, that means TV and phone, this section here has 21. So this plus whatever number here has to be 21. So we're going to put a 6. 15 and 6 gives us 21. We could also look at, let's do, now it's kind of up to you on what you want to do. They say both internet and phone service. So both internet and phone, they said 23. So these two together now have to be 23. So 15 and 8 makes 23. So I'll put an 8 there. Now let's say we can look at just phone service now if we want. We can say for phones, they gave us telephone service 32. So we need these three, and this is all the phone bubble here, right? These three plus a number have to equal 32. So these 3 plus 3 gives us 32. So we'll roll with that, okay? And you just kind of keep filling it in as we go. If we wanted to look at, now we could look at internet and phone or something like that, and then we end up with a 10 here. For internet, for just internet, they say we have 42. So that gives us a 9 here. So all 3 of these plus this number give us 42 that we see there. And the last number left for TV, a ton of people have TV service. This is probably old. Not many people have TV anymore, but they do. So we have 80 total in this big bubble. So we're going to do 80 minus all these guys gives us what we need, which is 49. Okay? If this were a problem and we had a sample where they had these customers or they were just taking a survey where these people had service and they surveyed 105 people and they gave us these stats and we put everything into the bubbles, but like 5 of the people had none of the services, then what we would be doing in that case, put this in a box and put a 5 over here. That indicates that 5 of the people in this case did not fit into any of these categories, okay? That's of course not the case here, but if it was, that's what we would do, and you would just roll with that. Now if we look at part A here, probability of cable TV only, if we only have cable TV, that means we're not intersecting with anything else, right? And we said we had 100 people, so it's just 49 out of the 100, so 0.49. So cable TV only, 0.49, 49 out of 100. If we had internet, given that we had cable TV in part B, internet given that we also have cable TV, internet given cable TV, how many people have cable TV? They said 80%. So whatever we have, it's going to be out of 80, right? They told us before that's our denominator, the 0.8. And then we also need to have internet and the cable. So that puts us with all of these guys here. These guys have internet and they have TV. So 25 total people out of that 0.8, so 0.25 out of 0.8, which is, if you do the math, around 0.3125, okay? So again, this is just, if we're looking at the probability of internet, this is called conditional probability, by the way, if you're looking for it in the book. I'm sorry. Oh, do you want the problem or do you want the math? Let's do that. Internet given cable. Then we have the intersection of internet and cable. I'm going to abbreviate here, internet intersect cable over just the probability of cable, right? And so the probability of cable, 0.8, internet and cable, 0.25. That's our 0.25. This is our 0.8. You okay with that? Conditional probability can get kind of funky, so if you still have questions about that, we can do some looking. But this stuff's really not too bad, and I'll leave these parts alone so we can keep moving and get to some of the harder stuff. Quick combination. A lot of you guys had to do counting rules this semester, combinations. Some of you guys did permutations and that sort of thing, or you had problems where it's like make a license plate and you have this many letters and they can be uppercase and lowercase, and you have all these different possibilities. So with the combination, some books write it like this, some books write it like this, different ways to look at it. Basically, we're going to read the problem here. So Jeannie has a list of 7 errands she needs to complete, but only has time to do 3 of them today because that's how days work. How many ways are possible for Jeannie to select the 3 errands she will complete today? So we don't care about the order. We're working with a combination. we know that our big N here, we can say is 7, little n is going to be 3, of course. And we know from before in our book, this is definitely in your book, we're going to have the big N over the little n times the big N minus the little n factorial. And so factorials, if we remember, if I write 5 factorial, that just means 5 times 4 times 3 times 2 times 1. And so these numbers can get pretty nasty pretty quick. Most calculators, though, especially graphing calculators, handle these really nicely. If you don't know how to do that, talk to a friend. If not, I'm going to show you how to do this one by hand real quick, because that's also a thing. So our big N was 7, little n was 3. So we're going to write 7 factorial over 3 factorial. We can all do 7 minus 3, which is 4 factorial. Now that, if we write it out real quick, because I don't have a calculator because I'm a horrible person, right? 4, 3, 2, 1 over 3, 2, 1. And this guy's 4, 3, 2, 1. Now I don't really care about the 1, right? Because we multiply by 1, it doesn't really make a difference. But what we can do is say this 4, 3, 2, 1 is in common with that 4, 3, 2, 1, right? And so now if I rewrite it again, we're just left with the 7, 6, 5 over the 3, 2, 1. 3 times 2 is 6, so 7, 6, 5, that was the denominator right here, over 6, those guys cancel. 7 times 5 is 35, and there's your answer, okay? Your calculator should get the same number. If it doesn't, either I'm broken or your calculator's broken, so it should be the same. I hope I'm not broken. That's how the math works for those. Those can be manipulated pretty heavily. They're not that hard to do by hand, sometimes. Other times you can work it down. If you have a scientific calculator that really hates these, it might be good to bring it down a few steps for it so that you're not working with such big numbers because they tend to get overloaded. I know most of your professors allow graphing calculators though, so shouldn't be a problem. In case you didn't know, the library, they have graphing calculators. You pay to use them, whether you use them or not. So you can go check one out. I believe they're on the 2nd or the 3rd floor IT desk. They have all of this equipment. You can just check out a calculator for a day. It doesn't cost you anything. So if you just want a calculator for your exam because you don't want to spend $100 on a graphing calculator, there's my advice for you, okay? Cool. Everyone get this? We're good? Awesome. All right, on to more fun stuff. So sample proportions, we've got p hats, population proportion p, just a notation thing. Now we're going to start looking at our normal distribution. These I'm sure you also had a lot of fun with, and they're very important because, as you know, we have to understand this in order to conduct hypothesis tests. Whether we're working with T or Z, we got to be able to read these graphs and interpret the probabilities. Tonight, I'm probably going to be working, not probably, I will be working off of the table out of the green book. I believe it's McClave and Sinsich. It's what most of you guys use. It's just called statistics. I know a lot of you guys have different professors who use different tables. Your table, I'll show you what we're going to be working with, might have a table that's, that has a negative side to it, which is totally cool. I like both tables. But this is the most commonly used table, so I'm going to roll with this one tonight. So if I do something process-wise and you're like, wow, I've never seen that before in my life, don't freak out. Try to use your table, the one that you have. Just because I use this doesn't mean it's the right way. It's just another way, okay? The tables, they work differently, but they get you to the same answer, or they should. So we'll be working with that. So quick practice. We're not going to do all these because my solution manual tonight will have them all on there, and you can zoom in and look at them. So we might just do a few of them. So I'll zoom in here so we can all read. But for this one, we're going to look at the probability of z being less than 2.36. So if we go way in here, bam. So if we go way in here, 2.36. Usually I like to draw a graph for all of these. We're going to label it real quick. 0, of course, is in the middle, negative to the left, that way, this way, positive to the right, this way. 2.36, I'll call it right about here, 2.36. And we want to know probability that z is less than this 2.36. So some of your tables, you look up 2.36 and you get a number. And that really tells you from the 2.36 down to 0 here. But I want to know all this, right? So if you have that table that gets you all the way down to 0, we need to add 0.5. If not, and your table is cumulative and you look up 2.36, it should just give you the number and that'll be your answer. But we'll see what happens. So reading our table, very important. Quick anatomy of your table review. Z's on the outside, right? So here is z of 1.6. This would indicate the probability of z being less than 1.66. Okay? So your tens place is here, and this is your hundredths place. So your z-table on this guy doesn't go any further than the second decimal. So you're never going to be looking for a z of 2.3794. You're just going to look for 2.37 or 2.38. Okay? So for this guy, we're looking for 2.36. So we're going to find 2.3. This is 2.30. 1, 2, 3, 4, 5, 6. Lovely. So that's our winner, 0.4909. If you have your table and you want to check it, go for it. If not, and you want to trust me, I mean, that's your choice, but we should be good. So we have 0.4909, which I'll put down here. And then we know that we needed to still add in this side here, that 0.5. So we'll add those together, and we should get, I believe, 0.9909. 9909, and that was from 0.4909 plus 0.5. Okay, and that's just nice and real quick. Notice, this is a key thing. It's a very conceptual question that you can be asked. When we're looking at this z distribution, it's what we call a continuous distribution. And what that means essentially is that the probability of z being any particular value, like just probability of z equaling 2.36, we call that 0, no probability of z just being a number. With this distribution, we're really looking at area under the curve. And if you're just at a point, I don't know if you've ever taken calculus or not, at a point, there's no area under it, so there's no probability. We need that range, like 2.36 down to negative infinity or something like that to give us that probability of 0.909 that we saw in the last problem. So the point of the difference between A and B here, these guys, notice this guy is just z less than 2.36. This guy's z less than or equal to 2.36. And what it's trying to get you to realize is that 2.36 for z by itself doesn't really have any value to it in terms of probability. So your answer for A and B will be identical, okay? And that's why we don't really care whether or not you write it like this or you write it like this. Those will have the same meaning, okay? So that's why the less than or less than equal thing doesn't really matter here, okay? Awesome. We can do, I'm going to leave the rest of these because my answers are all online. I'm going to give you one that's not on here. What's the probability of z being greater than 4.7? Just somebody out loud. That's a conceptual question. 0. Very good, right? Because if we were to give us a little graph here, 4.7 is like not even on the page. It's like over here, right? And there's nothing there in terms of probability, right? Same thing if we asked you less than 4.7, z less than 4.7, we'd be saying 1, right? Most of your tables, this one doesn't go beyond 3.0 or 3.9, rather 3.09. That's the max for this guy. Some tables go a little bit higher, so you might have to be a little bit more precise and you get 0.990 or 0.996 or something like that. But usually beyond 3.2, there's not much out there at all. And that should make sense considering we talked about empirical rule earlier. We said within 3 standard deviations, we have like 99.7 of our stuff, right? So anything further than that, there's not a whole lot probability going on in terms of that regard, okay? So I'm going to leave the rest of these because all my answers will be online. These can get kind of tricky when you're looking at the z naught and the x naught and the z, they write these things in a weird convoluted kind of fashion. So you know what, let's just come up with one. Let's do the probability of z being less than z naught, and that equals, let's pick a number, 0.378. That is totally random, by the way. So basically, this is asking, what's our z naught? That's what we want to know. There's a number that belongs here, and the probability of z being less than that number will be equal to this value. So essentially, this is kind of intuitive, but I know for most of us it's not, and it just comes with practice. But if the probability of my z being less than some number is 0.378, to me that means the area under my z is less than 0.5, right? So I can't be over here because the area below my number here will definitely be more than 0.5, right? If I'm up here, definitely more than 0.5. If I'm at 0, the probability of z being under me is going to be 0.5, exactly, right? So that tells me I need to be left on the distribution. I need to be somewhere right about here. So I'll just label that Z naught, and we'll just call it there. Now the area under me, they gave it right here, 0.378. So now I basically just need to find the Z that is going to give me that 0.378. So I'm going to sit with my table. Everybody take a quick minute. If you have a table on you, try to look it up, and we'll see if we all end up at the same answer. We want the Z naught here that gives us 0.378 below us. You might have to do some funky manipulation with this curve. Maybe you have to redraw it, so you could think about it being up here. And this will be a negative Z naught. We're definitely going to be negative down there. But this Z naught, we could draw it this way and have 0.378 here, which means we have 0.5 minus 0.378 here. I'm sorry if I'm going really fast. If you want to stop me, that's cool. I'm just trying to fly for you guys so we can get through as much as we can. So I'm going to do some quick math and see if I can come up with an answer, and then we're going to compare. Ready, set, go. Got to hide it, right? Yes, sir. Because that number is positive? Is that why you're asking that? Yeah. Okay, so this number here is representing a probability, right? We're saying the probability of Z being less than some number, right, is this number. So when we're looking at probability in terms of the curve, probability we know is always positive, right? Our probability is going to be between 0 and 1, right? But we know our Z, our table here, our little chart, these are where our negative Z's are on this side, positive Z's, right? So by that logic, if there's never going to be a negative number written here, because we're never going to have a negative probability. What indicates the side to me is how much probability is above or below me. The probability, this 0.378, that's an area within the curve. And I could have 0.378 sitting over here. I could have 0.378 sitting over here. It's the shaded part that is the 0.378. Okay? I'm looking for the Z that sits underneath the table, essentially, that's going to give me that area either to the left or the right. These two graphs here are equivalent. That Z will be the same. This one will just be positive. That one will just be negative. Okay? And this guy's really what matches this. The reason I did this was to give you that positive side for those of you working with the table that I'm working with, where we need to be looking at this probability, that 0.122. Hopefully you all got to that at some point, knowing we need that chunk in order to get the Z naught. Does it make sense why that this doesn't really determine which side of the graph I'm on, though, in terms of the sign? What's determining that is how much is above or below me in terms of this. Does that make any sense? Kind of, a little bit of nods. Yes? Good question. So Cassandra asked, when we consider adding or subtracting 0.5, does that just have to do with the probability, or does that sometimes happen with Z, where we're going to be adding or subtracting 0.5? Good question. So if we're dealing with that adding, subtracting 0.5, this is mainly the I'm working with the same table Justin's working people. You're only going to be dealing with that 0.5 addition subtraction when you're looking at the probability. We're never going to be adding 0.5 or subtracting 0.5 from Z. The only thing we might manipulate with the Z is the sign, positive or negative, depending on how we look at the table. Did anyone get a Z value for this yet, or no? What did we get? Negative 1.167. For this guy? Close. So if we had negative 1.167, I'm going to redraw this real quick. I'm going to draw it up here just because it doesn't matter which side I draw it on, the 1.167. Is that what you said? So first of all, my first question, how did we get a Z with 3 decimal places? Was it directly between 2? So what probability were we looking for here? For the Z? And so what were the probabilities for both of those Z's? 0.3962. So what that tells me is you saw an area here of 0.3962. What I think we tried to do was come up with this guy, or something as close as we could to it. Am I mistaken? Or is that what we were going for? Right, so that's what we got to look for. So this guy wasn't on the table. The problem with that methodology, and this is a very common mistake, not just you guys make it, believe me, I've done this like a zillion times. This probability here, that 0.378, I'm actually going to flip the page over so I can rewrite it for you guys. That way we're nice and neat. And the reason I'm taking so much time on this is I know these are common problems, and these are the most, if not some of the most commonly missed problems on exams. So that's why we're focusing on this. Also, it'll help you later with confidence intervals, hypothesis testing, all that when you have an unknown z. So we said before, we know our z naught's going to be negative. The area below me is 0.378. There's our negative z naught that we're going to be looking for. Now, when we look at our table, I'm going to rewrite this, an equivalent graph with the z on the right side. Not the right is incorrect, but the right is in right? So z naught will be here, and then this corresponds with this area. Sorry, they don't look perfectly the same, but they're close. 0.378 up here. Now, when we look at the table, for those of us working with tables like this guy, where it gives you from the z down to 0, this is from z to 0, if we notice that. On here, we have from the top to z. So we can't use the table to look from here to here. We're blind if we're looking at this. So what we need to do is find the area here from z of 0 up to z naught. We need that little range there. And the way we do that is we know this whole chunk, this whole half the graph is literally worth 1/2, right? 0.5. So here's where our addition and subtraction thing comes into play. We know we have 0.5. And I know that this much is sitting on top of my z to the right. So I'm going to subtract the 0.378, which leaves me with a whopping 0.122. Now, that area corresponds with here, just like we said, 0.122. Are we okay with how I got there in terms of manipulating the areas? That's one of the hardest things to do with these. But once you're past that, you're okay. Yes? No, same question. I just rewrote it. So we had the 0.378 above me here. I flipped it so that we're looking at the positive side because most people like positive numbers. 0.378 above me means 0.122 is below me to 0. There's another 0.5 down here. Remember, we didn't forget about that. But now we're going to look in the table for the probability of 0.122. So I take out my table. We look for not on the edges. This is the periphery is our z's. I want to know a z. I don't have the z. We got to look for probabilities. So I'm going to look and see as close as we get. It'll correspond here, 0.122. If we can see that, that's the area that we're wanting to look for. It just happens to be 0.122. So we're going to scour the table. Here's 0.08. Here's 0.11, almost 0.12. 0.12. Oh, that one's pretty close. And then this one is 0.1255. That's a little bit high, right? This is our winner. This is as close as we're going to get to 0.122, right? So now I want to know what's the z that corresponds here. We have 0.301. So 0.3, and this is not 0.301. This is just 0.31. This is our hundredths place, right? So I'm going to write that number down. 0.31. And that number corresponds with the z right there. But back to our original problem here. Our z naught, if we remember, it's going to be negative because we have this area below me. So all I'm going to do is just make that guy negative, that 0.31. So we're going to say negative z naught is equal to negative 0.31. And he goes right there. So now what we can do is just fill it in and check if you want to. So I'll just rewrite the problem, but now where z naught sat before, I'm going to put the z we got. Probability of z being less than negative 0.31, and that should equal 0.378. That number comes right down, and it should just go from there to there, okay? And so what I encourage you to do is look up this guy in your table and try to get back to where we started. If you get back to where you started, you know you did the right thing, which is what we can do. We can draw a graph real quick. label it. That's where z of 0 is. Z negative here, negative 0.31. And we want z being less than that, so we're going to look to the left here, this shaded region. This graph, for those of us working with a table like me, is the same as drawing it up on the top end. We'll have a positive 0.31 just so it's nice and pretty looking up here. And now this area also corresponds with, well, we don't really know yet. We're going to find out. All I know is that it should equal this, right? This shaded area should equal 0.378, okay? Now, if I look up the 0.31 in our table, we just went and did this, so I know it's 0.122, and that represents the area below the 0.131 down to 0. So this shaded region in there, that's our 0.122, okay? But this shaded region will be 0.5, the whole side, minus the 0.122, which will get us pretty close to our 0.378, right? We know this number wasn't perfect, so it's not going to be perfect, but it's as close as we can get with the table, right? So we have our 0.378 there, and that confirms that, so we are good, okay? Yes? So we didn't subtract 0.5 here. What we did is we went back to the table, we looked up the 0.31, which gave me the area from our 0.31 to 0, this section here. What I'm looking for is this section here from 0.31 up top. Same as here, 0.31 down low. Those will be equivalent, right? But the area my table gives me is this section, which is 0.122. So if I want to know this section, I have to subtract this from 0.5 because that's half the table. This whole half of the table minus the 0.122 gives me the shaded region of 0.378. And that's just a check mechanism. If you have time, great. If not, no big deal. Just keep moving, okay? That's a test-taking tip. If it's taking you 10 minutes to do a multiple choice problem, either something's not clicking, not happening, and that's okay. Just keep going. I wouldn't stop and waste 10 minutes on a problem. I'm sure most of you have exams. They could be in excess of 25 to 60 questions. It's anyone's game, depending on what your professor plans. Try not to waste too much time on any one problem. I would just keep the train going, as they say, and not get hung up on things that are either they're just not working, you can't remember, or you don't know what formula you're using, something like that. Just keep the ball rolling, and if you have time, come back to it. It's better to answer 3 more questions than try to keep answering the same problem. Yeah?
So is 0 always at the center of the
Yes, so that's a good question. Is 0 always at the center of this normal distribution? And yes, that is what our normal distribution entails. If we have this distribution, and I know it's symmetrical, we're working with z, right? It's a normal curve, then 0 is the z that corresponds with the middle here, right? And so positive z's this way, negative z's that way, okay? Good question. Does that make sense for everyone? Okay? Very good. Sorry for that brief delay. And now they're almost an hour in. I don't know if we will get all the way through everything. We will try the best we can, and we'll just keep going. I have a quick probability problem regarding binomial probability, if you want to review this real quick. It's asking about airline passengers and what they like to do on their flight. They're saying like 80% of people like to sleep and rest, and that's fantastic because that's what everyone wants to do. And what we look at with this is we basically start plugging and chugging into our formula up here. You might have seen this written a different way. That's totally fine. What I'm going to do is just do part A. That way we just get some experience plugging the numbers in, and then we'll roll from there. Just so I can give you a quick interpretation, and then you can do the rest on your own. They're really not that hard. You can also use tables for some of these, but the numbers have to match up. So your binomial tables, which look like this for most of you, binomial probabilities, have different tables. So you have different n values. N equals 5, 6, 7. You might go up to 25 or something like that. You need to be using the table with the right n, and make sure you're looking at the column with the corresponding probability that you're looking for. Some of your tables might be cumulative, meaning as you go down, they've already added in the previous ones for you. Others might not be cumulative, to where each probability given is just the probability for that specific x value. And so we'll just take a look real quick with the formula for this one. So they reported 80% of airline passengers like to rest or sleep. Suppose the actual percentage is exactly 80%. I'll zoom in for you so you can all see. And consider randomly selecting 6 people. X is the number among the selected who prefer to rest or sleep. And they tell us it's a binomial random variable with n equals 6 and p equals 0.8. So they give us this formula above, right? The probability of x being some number within our data set is just this n, our total number of things, right, over x, what we're testing for. And then p, they also gave us that. So they basically gave us everything we need. And so from there, I'm going to erase this so we don't see that anymore. And we're just going to start plugging stuff in. So for part A here, they just want to know probability of x being 4. So probability of x being 4 will equal 6 factorial. I'm just plugging everything into this formula here. Okay, this should be on your packet. 6 factorial over, looks like 4 factorial times 6 minus 4 factorial times our p, which is 0.8. They gave that to us right here, p. This is p of 0.8 to the x, which in this case is 4. Notice how those will change depending on what x you're looking for, times 1 minus p, which you might have seen written as q, probability of failure. That's another thing your book does. So 1 minus 0.8 will just be 0.2, so I'll write that as 0.2 to the n minus x, which is just 6 minus 4, or 2. We plug all those numbers in. It gets kind of pretty, and your calculator doesn't really like you, but it'll do it. 0.246 is our probability. So now what the heck does the number mean? That's tricky. Now, they told us x is the number among the selected 6 who prefer to rest or sleep. So the way we refer to this is that the probability of 4 of the 6 passengers like to sleep or rest on their flight equals 0.246. So in other words, you ask 4 out of these 6 people if they like to rest or sleep on their flight. The probability that all 4 out of those 6, that's their favorite activity, is 0.246, or about 0.25. Okay? We okay with how I just plugged stuff in? You might have seen this formula in a different way. It might be on your reference sheet in a different way. Numbers come out the same, I promise. You could see it with P and Q. Doesn't matter. Numbers work out. Okay? We good with math? Awesome. That's my quick binomial. On to some of the real fun stuff, right? Confidence intervals, which you all have grown to know and love. So basic form of a confidence interval, point estimate using a specific statistic, plus or minus the critical value, either z or t, depending on what we're working with, times estimated standard deviation of the statistic. If we follow that down here, we can see this is how I have it written. You might have seen it differently. It's okay. P hat plus or minus, there's our plus or minus, right? So we're working with P hat, that's our point estimate, plus or minus z alpha over 2, so this is for a confidence interval with z, okay, times our estimated standard deviation there. And that's just p hat times q hat. That's somehow times written as q hat, 1 minus p hat over n, the square root of the whole thing, okay? So, and they tell us here p hat is just x over n. So if I told you I surveyed 1,000 people and 876 told me that they like pizza, the proportion of those who like pizza is 0.876, okay? Just the number of people who said yes out of the total group, okay? For that, I want to take like a quick 2-minute break just as my throat is dying. So feel free to take a drink, use the restroom if you have to, and we'll be back in like 2 to 5 minutes. So go. Thanks, guys. Mm-hmm. Thank you.
So the previous question,
Yes.
6.1, you said that the numbers aren't on the table. You do that formula, but if they are, you could use the table.
Yes, you could if
So-
you wanted to.
Okay, so if like n is 6, and then you said 0.8, right, was the number,
Mm-hmm.
and then we went down to 4. We got 3, 4, 5 here,
Right.
but
So the problem here is your table's cumulative. So this really tells you 4 or less. So what this number means is the probability of x being 4, 3, or 2, or 1, or 0.
okay. So what we have to do in order to get rid of all those other numbers that we don't care about is on your table, we were looking here, right? It's either going to be, yeah, we're going to do 4 or less minus 3 or less. That'll leave us with 4. So you're going to do the 0.35 minus the 0.099, and you should get the same answer then.
Okay.
Okay, does that make sense? That's why those are kind of confusing, and it's really weird. Some tables work like that, some don't. That's why I'm like, I'm not going to show you how to use the table because you're going to get really confused.
Okay, now that makes sense because you're looking just for 4.
Exactly. If I had said probability of x being less than or equal to 4, then it would just be that number, and it's easy, right?
Okay, yeah.
So, yeah.
Okay, awesome. Thanks.
Yeah, of course.
Trying to keep up.
I know, I'm moving quick.
I don't know. I have C wrong. I don't know. I did P of 5 wrong.
X greater than or equal to 4. So for greater than or equal to 4, that's 4, 5, or 6, right?
Right. Yeah.
Okay.
So I probably just did something wrong for P5. But so how do I? So can I use a chart for this?
Yeah, you should be able to. You should have a chart for it. Yeah, it gets really, really nasty. And just remember, probability has to be between what? 0 and 1.
Oh right, yeah.
Yeah. So if you get
That's not
something like that,
possible.
something's going wrong. Okay.
Yeah. Okay.
Cool.
Yeah.
Yeah, and you'll see my look. I have all my work like this online, and you can see exactly what numbers I put, where the probabilities are. And so you did what, part C?
Yeah.
And that's what I got for that. If you want to write these down, you're more than welcome to, but it'll be online in an hour. So, okay, cool.
Can I see this page really quick? The one with
This
the Venn
page,
diagram.
it'll all be online. I'm sorry, I just want to keep going. Is that cool? It'll be on in like an hour.
The one you wrote, or like this one that's already done?
Everything, this exact thing, all of it done. I promise. Thanks, Lily.
Okay, cool. Who's ready to keep going? Awesome. Power through. So confidence intervals. We're going to look at this problem. It'll be lots of fun, I promise. Actually, I don't promise. It's going to be great. Probably won't surprise you to know that Valentine's Day, meaning big business for florists, jewelry stores, restaurants, you know it's a big day for pet stores. I didn't know that. Basically, people apparently like to buy Valentine's Day gifts for their pets. So they did a study. They did a survey. They asked if people were planning on buying gifts for their pets, right? So they told us all of this wonderful stuff. The proportion who responded that they did plan to purchase a gift for their pet was 0.173. That's important. Sample size for the survey was n equals 200. That's a pretty big sample. Usually we're assuming normality due to central limit theorem, which you've heard of, and that's just n greater than or equal to 30, right? That should sound vaguely familiar. Okay? Awesome. Moving on. So then they tell us to construct and interpret a 95% confidence interval for the proportion of all adult Americans who plan to purchase a Valentine's Day gift for their pet. So how do we do that? Well, we start with our formula right here. They gave us p hat. It's sitting right here. So we're just going to yank it out. 0.173. Done. Right? Plus or minus. We're just filling it in here. Z alpha over 2. We don't quite know this yet. You might know it, but I don't know it off the top of my head. Now we're going to plug in these numbers into that little set there. P hat, 0.173, times 1 minus 0.173 over n, square root of the whole thing. And our n, they told us before, was 200. So we'll throw in 200 there. Now, z alpha over 2, that's the tricky part. And what the z alpha over 2 depends on is our percent confidence. So if we have a 90% confidence interval, obviously a different z alpha over 2 than if we're working with a 95% or any other number. So for 95%, that's the equivalent of drawing something like this, 0 in the middle, and having a range here of 95.95, right? So that would leave us with what we call z alpha over 2, z corresponding with alpha over 2 right here, positive, and negative z alpha over 2 on the other side. And that means we had 5% left over divided by 2 because it's symmetrical, right? 2.5% in each one will be 0.025 here and 0.025 here. Okay? So from there, what we do is we look at our table. If we're working at a table that I have, we're going to need this area in order to find what we're looking for. So I know that 50% minus 2.5% is 47.5%, or 0.475. That'll be the area from here to here. I look at my table. And these are, of course, if you don't have the numbers on your reference sheet or something like that. And I want 0.475, so I'm going to just keep looking. Oh, there's 0.475. Look at that. I don't know if we can see it or not. 0.475. And that corresponds with a common number you've heard before in your life, 1.96. Okay? So that's my z alpha over 2. So I'm just going to literally plug that in here, 1.96. Now all we do is we do some quick math, we run some numbers, and you get an interval at the end. The way we write the interval is we write the lower number on the left. And notice we're working with a proportion. So our interval is going to be a proportion. Yes? Why are we looking for the 0.475? Good question. So this is, again, a table thing. You might not have to do this, but a lot of you definitely have to do this. So the 0.475 is because if I look for 0.025 on my table, that's going to give me a z that gives me from here to here an area of 0.025. But that's not what we have here. We have an area of much more than that below this z. And this is due to our table, right? So the area below the z to 0 here is going to be 0.475. That's just half the table minus the 0.025 or the 2.5%. So I need to have 47.5% below me, and that's what our table is going to give us here, because the area the table's looking at is from the z to 0, and in this case 0.475 will fit. Does that make sense? Yeah? Okay. Very good. So that's why we looked for 0.475. We found the z, 1.96, just like before. That'll become familiar if it hasn't already. Same thing with hypothesis testing. If you're working with an alpha of 0.025, depending on what type of test we're doing, or 0.05, one-tailed, two-tailed testing. We'll hopefully get to that soon. Otherwise, we're going to keep rolling. So 0.121 on the left, comma. This is how we make the interval, 0.225, and there's our interval. Now, in multiple choice format, you might not be, or you might be asked to interpret the confidence interval. Of course, we have an interval. These are representing proportions. So how the heck do we interpret this confidence interval? Now, all I have are these two numbers, but what I need to say here is something along these lines. We are 95% confident, okay? I'm going to abbreviate really heavily here because this is going to be online, that the proportion of adult Americans who planned to purchase a Valentine's Day gift for a pet is between 0.121 and 0.225. So what basically we're saying with 95% confidence that the proportion who want to buy their pet a gift is between 0.121 and 0.225. Now, the confidence does not mean probability. That's a very common misconception. You don't say there's a 95% chance that the proportions between these. There's no 95% chance that if you walk up to someone, then 12 out of 100 will say that they want to buy a gift. That's not what this is representing. This is just where we think the proportion lies based on that certain percent confidence. If we use a higher percent confidence, if I say do the same interval but this time with 99% confidence, do you think our interval is going to get wider or narrower? What do we think? Wider. Very good. Because if the interval gets wider, that means my z alpha over 2 is going to increase. I'm going to be pushing this z further out, making a bigger interval, which means this guy's getting bigger. And if this guy's bigger, we're doing plus or minus a bigger number, which makes a bigger interval. Okay? So if you have a pretty low percent confidence, interval's not too wide. If you have a really high percent confidence, interval is going to be wider, right? Another question you could be asked really quickly is they give you a confidence interval and they say, here's your interval, there to there. Now, what was p hat? At which point you might start screaming, but now you're not going to because this is very easy. If you want p hat, if you remember, all we did to p hat is we went up and down p hat, plus or minus, by that whole jumble of math that we did here, right? So p hat should really just be in the middle of these guys because it's just the difference between them in the middle. So if we want p hat, you just add these guys up, divide by 2, take the mean, right? And you should get right back to a p hat equaling 0.173. Done, that easy. Yes? Oh, I don't know what I just did. There we go, sorry. Good question. So how did I know that we had to use this formula to begin with? Well, the question when we started, they started with a p or a p hat. They gave me a proportion, right? And so usually these intervals are really done with, you know, x bar plus or minus something, or p or p hat minus plus or minus something, okay? So, and that has to do with our point estimate. Same thing with hypothesis testing. You're looking at p or you're looking at mu. Those are really your only two options, right? Or a difference between them. This guy, they gave us a p, so I know I'm working with p. They gave me a huge sample. That indicates normality, and that tells me go ahead and use z, right? That's how I was taught. Again, if your professor has different qualifications for when is appropriate to use z or t, that's cool. It might not be perfectly exact, but this is how I've done it. So we went ahead and used our z form of the confidence interval for p hat, okay? Formula will be slightly different if we were working with x bar or something along those lines. This guy will change up by a little bit. You might have it written differently, but that's why I elected for this. We were given a proportion. A big sample tells me z, and that kind of just narrowed it down, okay? Very good. Any questions on how I arrived down to the interval here? This is just a bunch of intermediate math. This is all button pushing, okay? Cool, cool. Awesome. There's another quick example down here. I'm probably going to skip it for now because we have like 45 minutes. This is a very similar type question. This is time we're going to be using a 99% confidence interval. So the only thing that's really going to change for you is your z alpha over 2. They give you a different proportion. Just use the proportion they give you. The only thing here was that p hat, remember, was x over n. In this thing, they tell us that they described the study where a sample of 52 young adults was looked at with pierced tongues, and then they tell us that in 18% of participants they had tooth loss or something like that. So I want p hat for the proportion of these teens that had tooth loss and had tongue piercings. So we have 18 out of the 52, okay? And we use that as our p hat of 0.346, okay? And so that's just the p hat you would use in your confidence interval when you go to construct it. Same formula as up here. And that's pretty much all we got there. Again, that's due, for my reasons, to 52 being our n, bigger than 30, normality z, okay? So that's my reasoning behind that. Quick math, if you want to write this down, you can. Again, it'll be available online, so no big deal, but that was the interval I ended up with for this one, okay? And I have the interpretations included in this. My solutions are not just like numbers, okay? There is writing. So you'll see it, and it should be very, very clear. On to hypothesis testing, because people tend to get tripped up here, just like in probability, but it's not too bad. First of all, type 1 and type 2 error. It can be kind of tricky, especially if you're asked, what's better for the company, you know, increasing type 1 error or increasing type 2 error, something like that. Type 1 error is denoted by alpha. You've seen that before. Maybe it looks prettier than mine, but same thing. Type 2 indicated by beta. Stats 1, we look at alpha because it's easy. Beta, you have to calculate. It's kind of nasty. We don't really deal with it in stats 1. But just know that as alpha increases, beta decreases. They're inversely related. So if you want a high alpha, you're going to have a low beta. If you want a high beta, you got to have a low alpha. Okay? And remember, alpha is just our probability of type 1 error. So if you're given a problem and they say use alpha of 0.05, and you go to do this problem, right? And one of the questions is, what's the probability of making a type 1 error? Don't think about it. Just pick the answer that is 0.05. It's just your alpha. That is your probability of type 1 error. Okay? It's really that easy. Type 2 error gets a little bit trickier. Just know that they are inversely related. If we make an error, either type 1 or type 2, type 1 is when we reject HO when in fact it was true. So we did an oops. We basically rejected HO, but we shouldn't have rejected HO. Type 2 error is the flip side. We concluded that HO is true when in fact it's false. So we didn't reject HO, but we should have rejected HO. Okay? So those are just opposites of one another. If you're allowed to write your formula sheet, I would just throw them on there. That way you have a reference. Maybe use an example, something like that. Your book is chock full of them, okay? But with regard to that, we'll keep pushing. So hypothesis testing strategies. First step, usually I like to do HO and HA. That's a really good place to start. Then I'll do our test statistic. So in this case, if we're working with P in our hypothesis test and we're doing Z instead of T because we have sigma or we know the sample size is big or something like that, and we're working with z, we'll do the test statistic, get our number for that. Then after that, we'll use either a rejection region, that's option 1, okay? So we can use a rejection region, that's one method, or a p-value, also known as observed significance level. Okay, those are synonyms. P-value, observed significance level. So if you see either of those are p-value. Okay, I'll just refer to them as p-values. One's not really harder than the other. They're just different ways of doing it. And we should come to the same conclusion, to reject or not reject. It shouldn't make a difference whether or not we do the p-value or we do the rejection region. We should get the same answer. And we'll see what happens with that in a few seconds. So with that being said, let's roll to this example. So, teens and distracted driving. We've all seen someone texting and driving, so this is relatable, right? Basically, they did a report on a representative sample of 283 American teens, 16 to 17, so young drivers. 74 who indicated they had sent a text while driving. Assume that this sample is a random sample so that we're meeting conditions, right? Do these data provide convincing evidence that more than a quarter of Americans ages 16 to 17 have sent a text message while driving? Test appropriate hypothesis using a significance level of 0.01. This is a synonym. Significance level is the same thing as alpha. Okay? Alpha is your significance level, which is not your observed significance level. That is different. Okay? Significance level, alpha. Alpha is our probability of what type of error? Type 1. Very good. Type 1 error is alpha. So alpha of 0.01. It's the same thing as 1%, but decimals are nice when we go to look at the curve. So step 1, let's look at HO and HA. We know that we're working with what? Do we have a P or a mu? Or an X bar? Or what the heck are we looking at? Any ideas? No? Yeah, proportion. Very good. So they want to know more than a quarter of Americans. More than a quarter of Americans. A quarter is a percentage. 25% of Americans. 38% of Americans. 78% of Americans. 78% of, the ice blocks sitting on the floor that are in Florida for whatever reason. Whatever it is, a proportion is always between 0 and 1, right? Just like our probability values. And it's just representing a fractional amount. So in this case, they want to know, is there convincing evidence that more than a quarter of Americans with this age sent a text, whatever? So when we write our HO and HA, we know we're looking at a proportion. So these will both be P, not P hat, P, okay? These guys will either be P or they will both be mu if you're working with a mean, okay, for HO and HA. You can be asked which of these is the correct HO and HA for this hypothesis test. That's a common multiple choice question. It could be really that simple and you just have to identify the right one. The reason this has any sort of trickery in it is that they didn't give us a number. They told us a quarter of Americans. So we have to use our noggins and say, what is a quarter? Oh, a quarter is 1/4. So we're just going to use 1/4 for the P, okay? So HO, we always have this value equaling the value we're looking at. It'll be the same for HO and HA, that 1/4, 1/4. And so the alternative hypothesis is, wow, we want to see, is the proportion more than a quarter, right? So greater than. So this will indicate what type of rejection region. We have one-tailed upper, one-tailed lower, and two-tailed. What do we think this one's going to be? One-tailed upper. Very good. Upper indicated by greater than. If this was less than, we'd be at one-tailed lower. If it was not equal to, that's a two-tailed test, right? So we're looking at an upper-tailed test. Now, on to our test statistic. Now that we've done that, I'll just write TS for test statistic. And we're just going to basically use the same formula that we had up here, okay? So we will have our Z, test statistic Z, equaling our P hat. Ooh, they gave us a thing in here. What's our P hat? We don't know yet. Well, we know what P we're looking at, that proportion, but how do we know what the P hat was? They said they had a sample of 283 American teens, and 74 indicated they'd sent a text. So the proportion who indicated they've texted while driving or something like that was 74 of them out of 283. So that's our P hat. So when we're filling in our formula with the P hat, we're going to be using that 74 out of 283. So we have 74 out of 283 minus, this is the P naught, essentially, what we're testing for, that 1/4, okay, over the square root of P naught times 1 minus P naught, so 1/4 times 3/4, right? That's just 1 minus a fourth. Excuse me, 283 for our n, right? And that's just from over here. Our n was 283. They gave that to us subliminally, kind of. So we filled in all of our numbers. We do math, ready, set, go, and I got 0.45. Hopefully you get that too, okay? So that's what my math came out to. So our z for this test statistic is 0.45. Now on to rejection region. We've done our test statistics, so now we're going to see, what are we going to do? Are we going to reject HO or not reject HO? Remember, those are our two options, unless your professor has told you a different way, which is possible. Highly unlikely, though. Like, I'm talking like probability less than like 0.05, okay? You either reject HO or you don't reject HO. It's very cut and dry in terms of how I was taught to do it. Either you reject HO or don't reject HO. We never accept HO. We never accept HA. We never reject HA. We never say HA is great. Like, none of that. It's either reject HO or don't reject HO. So those will be one of the things that we say at the end of all this. We write our rejection region. In this case, we'll use a rejection region. I'll draw a little curve just for me. You don't really have to, but I like to because images are nice, for me at least. And now, what the heck are we going to do? Well, alpha, our probability of type error, they told us was 0.01. And we know that we're doing this one-tailed, upper-tailed test from before because we were looking at greater than here. So if we're at the top end here, I know that there's a tiny little shaded chunk of my graph, and this little shaded chunk is equal to my probability of type 1 error, or alpha, of 0.01. Okay? So now, essentially, I need to know what z corresponds with alpha equals 0.01. What is the z sitting right here? And how do we figure that out? Well, we have to remember how to read our table from before. If you're working with a table like I am, then I need to know this area. If this is 0.01 and the whole right half of the graph is 0.5, then how much is in this big chunk here? 0.49. Beautiful. So that was just 0.5 minus the 0.01, or 49%, 0.49, right? So this 0.49 is what we're going to be looking for in my table. So we take out the handy-dandy table. Feel free to do this so you get practice looking at what z we're working with. But if we're looking for 0.49 on this, how close can we get? This is 4898. That's pretty close. Ooh, 4901. That's even closer. Yeah, that's about as close as we're going to get. This is too far, right? So we're looking at here, we have 2.30123, 2.33. There's my z, done, okay? Yeah, I have some practice with this, so it doesn't take much time. But once you do 3 or 4 of these, it's really not bad at all, okay? So that z alpha of 0.01 will be 2.33. Now, what we want to compare, this is fairly simple. It doesn't require much thought. Basically, I want to know, is the z that I found before with my math, is this in this shaded region or not? That's why it's called a rejection region. If it's in the shaded part, it will be, we will reject HO. So sometimes I'll write another statement just to like not trip myself up and I make sure I know what I'm looking at. I'll say if, we'll reject HO if z equals 0.45, what we found in our test statistic, is greater than z of alpha equals 0.01, which is 2.33. So now I'll rewrite this. Is 0.45 greater than 2.33? Yes or no on 3? 1, 2, 3. No, it's not. Good. So this is a false statement. And if it's not false, if it's not true, it's false. And that means this is not in our rejection region. That makes sense, right? 0.45 for z would be like down here, right? Not in our rejection region. And if we're not in the rejection region, then we say, do not reject HO. Okay? And that'll be the start to our conclusion. The full conclusion I have, it'll be posted online, but I'll just read it aloud so we don't write it all. We'll say, don't reject HO at the alpha equals 0.01 significance level. That's important, because if we test this at a different significance level, we very might well have a different conclusion. We might end up rejecting. And that's what happens in life if you're doing stats. you manipulate that alpha. You decide that alpha when you run this test. So you might decide to reject one way, but not with a different alpha. But for this time, we're not rejecting. So at the alpha of 0.01 significance level, there's insufficient evidence to indicate that the proportion of Americans ages 16 to 17 who have sent a text while driving exceeds 0.25, or 1/4, what we were testing for before. So it's kind of weird. You get used to it, though. Definitions and the conclusions are not too hard at all. Any questions on this process-wise? Very good. Yeah, my guess is if we still leave 15 minutes at the end, we're probably not going to get through all this, but that is okay. You'll have plenty of practice. And like I said, all the work will be out there online, so it won't be bad at all. We have a couple options. Do you want to see us, would you like to see us do that same thing but with a p-value, so we get used to p-value, or do you want me to do a quick two-tailed test with p-hat? Show of hands, who wants the p-hat new test versus p-value? P-value it is. Cool. So let's go here. Quick thing on p-values, okay? That other problem will be online, so don't worry about it. We'll make sure you get your info. So p-value or observed significance level, it's another way to test, like we said before, versus the rejection region. If we're looking at a one-tailed, upper-tailed test, these all work the same way, by the way. Greater than, upper-tailed, less than, lower-tailed, differs from, two-tailed, same thing. The p-value will be p probability of z or t, depending on what you're using, whether it's z or t, doesn't really make a difference. For the upper-tailed, greater than the test statistic. This will make more sense soon. For this guy, same thing, except this is less than. For the two-tailed, you're looking at 2 times the probability of z or t being greater than your test statistic. That 2 times is important for that two-tailed test. Real quick, if we look at this same exact question, same 0.45, but now we got to run this thing with a p-value. So with this p-value, we are still looking at a one-tailed, upper-tailed test, so we're going to be referencing this guy here. So our p-value will equal the probability of, in this case, z, because we're using z instead of t, probability of z being greater than our test statistic. And remember, that was just 0.45. We did that math already. So all of your work up to the p-value is the same, whether you're using a rejection region or not. So the probability of z being greater than 0.45. Now, you look at your table, you look up the numbers, and you determine that the probability of z being greater than 0.45 is equal to 0.3264. Okay? So you get this number. That's your p-value. Simple, right? This is your p-value. Remember, because the p-value equals this statement here. Okay? So the way the p-value works, you're still going to either reject HO or don't reject HO. But we make that determination using this p-value, and we compare it to our alpha. We still had an alpha here of 0.01. That's great. So the way this works is as follows. If the p-value is less than or equal to the alpha, we'll reject HO. If that is not a true statement, we don't reject HO. So what's common is big p-values you don't reject, because alpha is usually tiny, right? If you have a big p-value, you're bigger than alpha, you're not going to reject HO. If you have a tiny p-value, say 0.001, you're probably going to be rejecting, because alpha is usually between 0.01 and 0.1. Okay? So in this case, our p-value was 0.3264. We're going to compare it to alpha. Basically, I want to know, is 0.3264 greater than our alpha of 0.01? True or not true? Yeah, it's true. So this is bigger than this. This is our alpha, right? And if this is bigger than alpha, we do not reject HO, because p-value is greater than alpha, right? Okay? Same conclusion. That's important. That's what I said before. The p-value approach versus the rejection region approach, same conclusion. Yes? I don't know if I missed it, but how did you get the 0.3264? This, I skipped a step because I'm a meanie. That's what this represents, okay? If you look up the 0.45 in your table, you're going to get like 0.1736 or something like that. That is representing the probability you don't want. You need to do 0.5 minus that, okay? And that gives you this 0.3264, okay? So that's how that works. That's just a normal Z-type question, just like we looked at before. That's why I said that's important, okay? Good on this? And that's the big takeaway thing. P-value should have the same conclusion. So if you run a hypothesis test with your rejection region, you decide, yeah, reject HO. And then you're like, wait, but like, should I? And then if you have like 20 minutes on the clock and this is your last question, just run it with a p-value. Just give it a shot. Try to check it, and you should get the same conclusion. If that's not matching up, then something went wrong somewhere, either with your p-value or your z. It's at your discretion, but they could very well ask you, what's the p-value for this problem? And that's it. Like, you just got to find the p-value. Then the question right after that is, do we reject HO or not? Which you got to make a determination based on, of course, what helps us determine? We got our p-value. What do we compare it to? Alpha. Yes, exactly. P-value less than alpha, reject HO. P-value bigger than alpha, don't reject HO. Yes?
When would you use p-value over rejection?
If they tell you to. It's really up to you. So Artur's question was, when do we use p-value over the rejection region? Well, it's usually at your discretion. If you're told to use a p-value because you need to find that for your answer, use a p-value. If you don't need to use a p-value, you don't have to. If you're comfy with rejection regions, do what makes you happy. I don't know. They could ask you, I mean, what's your z critical value, or what's z alpha of 0.01 for this problem, or just z alpha over 2 in general for a two-tailed test, in which case you would have to be using a rejection region or something similar so you get that z value. Otherwise, I mean, p-value is cool too. It's just another way to do it, okay? Cool beans. Let's see, what do we have next? I have confidence intervals with x bar if we want to do them. We can do that if we want, or I can do a quick test, a hypothesis test with mu using t. Does anyone want to get some practice reading a t-table, or do we want to do, yeah, I see nods. Cool. Hypothesis testing it is with t. So this is what I learned in stats when I took stats, right? The test statistic for mu, when we knew sigma, we would use z. If we didn't know sigma, we would use t. That is most likely, I say most likely because I've seen this a lot with you guys who've come to tutoring before, that's not the case, where there are different qualifications for your professor. Like if you have a big N, just go ahead and use z, which is cool. Just do what you got to do. This test might be one of those things where, you know, that's the deal we have. I ran it with t. Just do it so we can get practice with t. And then if you want to, go ahead, give it a shot with z and see what happens. A lot of the time, if your sample's big enough and you're rolling off that t table, and your n gets really big, your degree of freedom gets really big. And when that happens, you're really just looking at a z value if you're looking at infinity row, right? The fancy infinity row. So with that being said, we'll give this guy a crack. I'm going to let you guys read for a second, and then I will highlight some important values. Looking at money. Okay, wonderful. So we're looking at a test with mu. I already told us we're going to be going with the t value here. The reason I would be using t is because they tell us something here that's fairly important. They say mean offer of this and a standard deviation of 3,300. And they told me it was a sample, so sample standard deviation. So I would be using t. That might not be the case for you, but that's okay. We're just going to do it with t. We'll all survive. And then what's the first step of our hypothesis test? What do we have to do first? HO and HA. Awesome. So we're going to do HO and HA here. HO, HA, just like usual. We're working with, in this case, what do they tell us? We're working with a mean or a proportion? Mean. Very nice and obvious. So mean indicated by mu. These will both be mu, right? And then HO, we know mu is always going to equal something. And in HA, we got to see what the heck they were asking for. So they want to know, do the sample provide strong support for the claim? Here's our claim, right? That the mean salary offer for accounting grads of this university is higher than the 2010 national average of 48,722. Okay? So that means in my HO and HA here, what do you think our sign will be for HA? Are we going to be looking at not equal to, greater than, less than? What do you guys think based on the wording? Greater than, right? We want to know if it's higher, right? So if higher means more than, which means greater than, which means write that thing. So we have our greater than. Now we know we need the same number here for both of these guys. And what is the mean that we're trying to see if we're exceeding? What do we think? Conflicting answers, right? We're going to be looking at that 48,722 because that's the national average we're trying to compare to. We want to see if we're going to exceed that. So we'll work with the 48,722. Good, good. Now we did HO and HA, on to the test statistic. And for this guy, we'll have t equaling x bar minus mu naught over s over root n. Sample standard deviation, our sample size, right? And this mu naught, that's basically what we have sitting right here. The x bar is the sample mean. So they looked at the sample, right, and they got a mean of that. That's your x bar, 49,850. Okay? So we've got that. Now we're just going to plug and chug here. Mu naught, that's just what we're testing for here, the 48,722. Any confusion about where numbers have come from so far? Just so I can clarify if we need to. Wonderful. So we're going to plug stuff in. 49,850 minus 48,722 over, oh, we need S. Where's S? 3,300 right there. Sample standard deviation. So we have 3,300 over root n, and in this case our n was 50. You do math, you get 2.417 approximately, right? So we get something like that. Now we can do this with the rejection region, p-value, whatever. Let's just do it with the rejection region. That way we get some practice with the wording. Rejection region, nice pretty curve. There's 0. Now one thing we need to look at here when we're making this rejection region is what's our alpha? Alpha is 0.05. Good. So we know we're doing a upper tail test. You guys already told me that, which is awesome. So on this graph, we've got the 0.05 up top in our upper tail. So we got our tail, 0.05. Great. Now, when we look to find our corresponding z alpha equals 0.05, the z that gives us that alpha right here, we're going to be looking at what's left here, which is 0.45 in most of our tables. Some of you don't have to do that, but most of us do. So we're going to look for the z that gives us that 0.45, and that will be, oh, I'm sorry. Are we doing this with z or are we doing this with t? T, good question. Man, you guys should have been like screaming at me. I should have like pitchforks thrown or something. No, I'm just kidding. So if we're looking at t, we still need to know the corresponding t value in order to make our rejection region. The rejection region will look pretty much the same. But we got to know this t value thing going on. So that t usually takes the form of a t with a degree of freedom equal to n minus 1. And alpha is still 0.05. We know that, right? So if we look at our table here, we find our t table. Notice it is not your z table or your normal curve areas. A lot of you guys, it'll look something like this. Critical values of t. In this case, we had a sample size of, I think we were looking at what, 50? Yeah, just 50. So with this thing here, the whole degree of freedom stuff going on, notice how on this table, they're all different, but on this table, this goes up in the ones up until 30, and then jumps to 40, and then to 60. 50 is smack in the middle, which is wonderful. That makes things really complicated and annoying, but that's really okay. We're going to go down in this case. Usually things get truncated or rounded down if you're in the middle. So 50 between 40 and 60, we'll go down to the 40. That way we're not overestimating this or something like that. If I was at 55, I would be picking the 60. If I was at 42, I'd go down to the 40 anyway. Just kind of get as close as you can. If we're over that 120 mark, if you're pushing 150, 160, 180 for your degree of freedom, then you're looking at the infinity row here. And this infinity row is actually just z-scores for the corresponding t's. So notice that should look familiar, 1.645, 1.96, 2.33, 2.58. Those are all familiar numbers that you've probably seen before, and those are straight off your z table. Because as that sample gets so big, t goes to z, and you get that z value. So for this guy, we said we're going to look at the 40 column here, and then we know our alpha. This is nice and handy, right? They literally just put alpha on the graph. So if we want an alpha of 0.05, so t of alpha equal 0.05. So we look at this row. If it was anything else, you would pick another one, okay? So 0.05, we look down, and we were going to look at 40 here. So I'm going to pick the 1.68. That's our magic number. So 1.684. We'll roll with that. So I'm going to say my t is 1.684. Good, good. Now, we do this the same way. That t, we'll just kind of throw it right here, 1.68, okay? And now we want to know, do we reject or not? That's the question, right? So we will reject HO. Write it like this. We'll reject HO if t of 2.417, just like we have right here, see, that's our number, our test statistic, is greater than t of alpha equals 0.05, degree of freedom equals 49, which is 1.68, okay? So basically, I want to know, is 2.417 greater than 1.68? Quick yes or no? Yes. Wow, you got, everyone's going to get an A now. So 2.417 is bigger than this guy, so we're going to go ahead and reject HO. This should become obvious with the graph, right? Here's our 1.68. We found that on the t-table. Our test statistic was 2.417 up here. So I know 2.417 is way bigger than 1.68. It's sitting in the rejection region. It's called that because we reject if it's in the rejection region. So we will reject HO. And the conclusion will be online. Basically, there is sufficient evidence at the alpha equals 0.05 significance level to conclude that the mean salary offer for accounting grads at this university is higher than the 2020 national average of 48,722. Basically, just throw all the numbers in that you started with, and you write the conclusion. It's not too bad at all. Does anyone have questions on how I ran this test with that T? I'm assuming people just needed practice reading the table, but I know you guys have done this countless times in class, so it's really what it should be, a review. Any questions on that? No? Okay, so we've got exactly 16 minutes-ish. So now is the time where I ask you guys, do you have specific questions on stuff? There is more in this, obviously. There's a bunch more. If you want to keep going, that is fine with me. We'll maybe get through like one of these because these get kind of big. This is newer stuff though. The reason I did it this way is because I figured old stuff is old and new stuff is fresh. But if you guys are struggling with this stuff, I'm happy to do one where we have something like a large sample confidence interval for a difference in proportions. If not, I will take questions. So does anyone have questions? Yes. Margin of error, yeah. Let's see if I think I pulled up a problem for you guys for margin of error. So if I'm looking at margin of error here, we can look at a problem similar to this. And so I already have a lot of this stuff written out already. So I'm just kind of walking through it real quick. Sorry, it's on a screen, so we'll see how bad the glare gets. Okay. We good? Yeah? All right, sweet. So if we're looking at this, basically there's an article, 9 out of 10 drivers admit in a survey having done something dangerous. That's incredibly vague. Reported on a survey of 1,100 drivers. Of those surveyed, 990 admitted to careless or aggressive driving during the previous 6 months. That is a massive amount of people. Assume that the sample of 1,100 people is representative of the population of drivers. So they ask us to do things. Some of this doesn't really apply to what you were asking, which is okay. This was just calculate p hat. This was see if we're representative. This is just nonsense for you guys right now. C was calculate the margin of error. Now with this guy, we're looking at a proportion. A general formula we used when we took stats was that the margin of error is just this. 1.96 times the root of p hat, 1 minus p hat over n. And that's just 1.96 times the standard deviation or the estimated standard deviation of the proportion, okay? That's similar to what you saw in a confidence interval when we looked at a 95% confidence interval. That's a very common way this is written. This could change theoretically depending on the problem, but this was our go-to when we did these sort of problems. I would just reference the chapter on margin of error, look at some of the formulas you have, but for this sort of problem, we would literally just plug the numbers in. So 1.96 p hat we found up here in part A, the 0.9. Plug everything in. The n, they gave us 1,100, and that would be our margin of error. And so the interpretation of this is kind of weird, but we can look at it. And so we say that it's unlikely, well, we can look at what they asked. In D, interpret the margin of error in the context of the problem. We would say it's unlikely that the estimated proportion of drivers who admitted to careless driving in the last 6 months differs from the true proportion by more than 0.0177. That's what it means to have our margin of error, okay? So we're not expecting the proportion to differ by more than our margin of error, okay? If that makes any sense. Is that okay for margin of error? Okay, cool. Any other specific questions? Yes? It's a Z, it's not really a t-value. It might be on there somewhere if you look way down on the degrees of freedom. That was just our standard number. It is not the only number to be used. It's just with a certain expected percent confidence or something like that. That's usually what we used, yes. It doesn't have to be that, though. Good question. Yeah? Yeah, so the question was, isn't that 1.96 for a confidence interval? Yeah, it's really just a Z. So it is used in confidence intervals. It represents a certain level of confidence for those. But otherwise, it might just represent a certain proportion that we expect to be within a certain range of the mean in terms of the probability. So that it really could take on whatever meaning it is in context of the problem. Okay? Any questions on that? Any other topics that you guys were freaking out about or you're not so comfortable with? Yes? For this margin of error thing, or for the hypothesis test? Let me see. Mm-hmm. This question, yes? So your question was what changes? I'm sorry? What part changes? If the sample is less than 30. So for most of you guys, yes. If the sample is less than 30, a lot of what I've heard your professors are saying is if the sample is less than 30, then that's not enough to assume normality based on central limit theorem. So if you're not given a population standard deviation, you're going to be working with T. But a lot of your professors would also say, big sample size, we're bigger than 30, go ahead and use Z and assume it's normal. So it could go either way. That's why I always say just check with your professor on what they think is good. In terms of the rules, guidelines, how you would go through the process, depending on sample size, depending on whether or not you know sigma, depending on the qualification for normality if you're working with P and you need n times P to be greater than or equal to 15 or n times 1 minus P to be less than or equal to 15. That's one thing that your book says to assume normality. Those are just a couple of items there. Yes? How do you know which formulas to use for each question? That's a tricky question. It depends on a couple of factors. So one, are we looking to generate a confidence interval or are we looking at a hypothesis test? For confidence intervals, you have 2 or 3 main go-tos. Well, really 4 if you think about it, because we have confidence intervals with P, right, proportions, and we have confidence intervals with X bar or our sample means, right, means. And then we could use a Z or a T for confidence interval over here with our P's, or a Z or a T here with our mu's or our X bars. So that's another distinction. Then you have samples where we're looking at comparing 2 samples, a difference in P's or a difference in Z's, or not Z's, I'm sorry, or X bars. So in a nutshell, it's really hard to give you an exact answer of when to use what, but usually the determination is based on sample size, whether or not we can assume normality, whether we're working with P or we're working with an X bar, something along those lines. And then if you're running a hypothesis test, maybe you're working with mu. And those are just a couple of the factors there. I'm sorry if that didn't totally answer your question, but that's why I usually encourage you to ask your professor. Yes? You mean p-values in like a probability? No, I'm sorry, it's okay. Yes. Okay, gotcha. So I'm assuming that your z-table has a positive and a negative side, correct? So in that case, I'll give you an example here. If we're looking at our table, the question was with regard to the z table, how we interpret the probability when we find a number. So say I look up z of, I have a 1.70 z. Then that means my probability here for this table is 0.4554, which represents from 1.7 down to 0 for this table. Okay? For your table, it would give you the 0.4554 plus 0.5. It would give you all the way down to the left side. So you would have 0.9554 if you looked for a z of 1.7. Is that what you see there? Very good. So that would represent the probability, I'll write right on this, the probability of z being less than 1.7. But if I asked you what's the probability of z being greater than 1.7, now what happens, I need to look this way, which your table doesn't tell you. Unless you have options. You could look at the probability of z being less than negative 1.7, which will give you the same answer as if you find this guy, the probability of z being less than 1.7 and subtracting it from 1. Those will be the same. This is equivalent to 1 minus the probability of z being less than 1.7. Those are equivalent, okay? Those graphs, this guy. If this guy, we have 1.7, less than that would be this shaded region. 1 minus that, right? This statement, 1 minus that gives you the small shaded region, right? And this guy, you have negative 1.7 way out here, and that small shaded region, same small shaded region. The probability is worth the same amount, okay? It's just whether or not you looked at it negative or positive. Okay, so it depends on the flexibility of your table. These guys might take a little bit more thinking. That table is actually, I like the plus and minus table better, but it just depends on what your professor gives you, okay? Does that kind of answer your question, how you can play around with it? Yeah. Okay. Good, good. Any other quick questions? We have about 5 minutes. Up to you guys. I know it's been a crazy semester with the hurricane and everything, but it's been great seeing most of you in SARC. A lot of really familiar places, faces, and some really cool stuff going on. It's been a pleasure all semester with you guys. If you don't have any further questions, that's fine. But I'm more than happy to run through something real quick in the next 5 minutes and give you a breakdown of a quick difference in P's confidence interval. That's more of a new thing, but I'll give it a shot for you. If you want to leave now, that's totally cool. If you do, please go ahead and do the survey at the end of the tables. Don't worry about turning it in. Just leave it there. I'll come around and pick them up. Okay? Please be as honest as you can. I want to know how I did. I want to know what you think of SARC SI, Student Development and Enrollment Services, how we put this event on. For everyone on the live stream, thank you for watching. And we'll give this one quick last problem, and then we'll be good for the evening. And I wish you all the best of luck on your exams. Sound good? Muy bien. Thanks, guys. Okay. So this question is just a quick look at a large sample confidence interval for a difference in P's, or proportions. This is our formula. You've probably seen one that looks very similar. This might be written as Q hat 1, Q hat 2. Just depends. Thank you, guys. And then these are your conditions down here for what happens once you run this. So if you want to know this, or you have one that's greater than the other, this just gives you a breakdown of what everything means. I'm not going to get into depth. But it's just an explanation of if your interval has two positive numbers at the end of it, then that's telling you that the P1 that you assigned is bigger than the P2. If they're both negative, then P2 is bigger than P1. And if you have a negative number and a positive number for your interval, that interval contains 0. And we say that there's really no difference in the proportions. Okay? So this is all about trying to find a difference in proportions for two different samples. So for this question, we basically, we see how people react to asked if they're expected to get a raise or a promotion this year and what they think. So 52% of men said, yeah, I think I should get a raise, and 37% of women said, yeah, they should get a raise. This was something from USA Today back in 2012. So it's a summary of things. Basically, step one when we go to do the confidence interval, define P1 and P2. We're going to do proportion of men and proportion of women. Proportion of men, this will just be men who expect a raise this year. and that was 0.52 from this little diagram here. Women, women, same thing, equals 0.37, okay? So that's our proportion of men, proportion of women. I'm going to do proportion of men minus the proportion of women because I like positive numbers when we subtract these. So I'll say the proportion of men minus proportion of women, plus or minus, we're going to use z because this sample had like 507 people, so we're going to assume it's normal. Z alpha over 2, they said let's 95%, so alpha over 2 was 0.025, which means we are just going to have, this guy will be 1.96. That's just a 95% confidence interval, 196, okay? Times this whole test statistic stuff, not test statistic, but formula, and then you'll have 0.52 times 1 minus 0.52 plus the other proportion. We're just filling them into that formula we saw up here, that guy. Divided by their individual n's. This guy had, they both had 507 under them, both samples. And then we had these subtracted from each other here, 0.52 minus 0.37. And that was plus or minus all of that stuff. We do some math, we get an interval of 0.09 to 0.21. And so the interpretation for this guy is simply that we are 95% confident that the proportion of men who expect a raise this year is between 0.09 and 0.21 greater than the proportion of women. That's what it means in the context of this problem. That goes back to this up here. Both numbers were positive, so the first number we used, that p hat 1, must be higher than the p hat 2. Notice our p hat 1 was males, p hat 2 females. So the men think that, or a higher proportion of them think they're going to get a raise compared to the females in this question. Anyone have a question about interpretation or anything on that? Cool. All right, well, we are right about out of time, so it's been great being with all you guys. I hope you have a safe trip home. Study up. If you have tests tomorrow, best of luck. Tests this week, also best of luck. I know I have 3 exams tomorrow, so I will be studying right along with you guys. Enjoy the student union because we're open 24 hours. If you want access to the live stream, like I said, it should be up within the day or so. Feel free to check out the Stark YouTube channel. Lots of helpful videos. Check out the other study union sessions going on throughout the week because we got tons of classes covered. So thank you so much, everyone. Have a great night. Thank you.